Welcome, everyone. Thank you for being here today. I'm Bill Sanders, Strecker Dean of the College of Engineering. Last fall, the College of Engineering kicked off a new webinar series entitled Faculty Insights, a 20-minute briefing, which we're holding every other month. In this virtual series, faculty from across the College of Engineering will share insights into their research, its impact, and provide a perspective for the future. Following each 20-minute presentation, attendees will have an opportunity to direct questions and comments to the speaker. Our speaker today is Professor Burak Kara. He's a professor of mechanical engineering here at Carnegie Mellon with a courtesy appointment in the Robotics Institute. Burak is also the founder of Visual Design and Engineering Laboratory. His research interests include computer-aided design, computer graphics, natural user interfaces, and machine learning, with applications in industrial product design, automotive design, engineering education, and biomedical engineering. Burak is the recipient of a National Science Foundation Career Award and an American Society of Mechanical Engineers Design Automation Society Young Investigator Award. At CMU, he teaches courses in AI and machine learning, engineering design, linear algebra, and vector calculus. Burak has a BS in mechanical engineering from the Middle East Technical University and an MS and PhD in mechanical engineering from Carnegie Mellon University. Today, Burak will be talking with us about artificial intelligence and machine learning to accelerate product design, simulation, and manufacturing workflows. Burak, thank you for being here today to share your research insights. Before I turn things over to Burak, please submit any questions you have in the question and answer feature at the bottom of your screen. So there's a button there you can use at any time during his presentation or afterwards to submit questions. Nikki Wolford, the Senior Associate Director of Development for the College of Engineering, will be moderating the question and answer session with Burak at the conclusion of this presentation. So Burak, I'll turn it over to you. Thanks for being here, and thank you all for participating today.
Bill, thank you very much for that very nice introduction. Good afternoon, everyone. My name is Burak, and I'll be talking to you about my research over the last 7 to 8 years in the space of engineering design, focused mostly on mechanical engineering design and its applications where we're using AI and machine learning to accelerate the design and synthesis and analysis of interesting products. In today's talk, I'll be focusing mostly on additive manufacturing, my research surrounding additive manufacturing and geometric modeling, shape design. But if you're interested in further applications of machine learning, I invite you to visit my website, which will be available to you at the conclusion of this talk. So let me share my screen and then we can get started. All right. So in the Visual Design and Engineering Lab, we bring together 3 major disciplines in mechanical engineering and computer-aided design with product design and AI and machine learning. As you will see in the upcoming slides, a lot of what we do involves shape design, shape analysis. So there's going to be a lot of visuals in the upcoming slides. So hopefully it's not going to be a boring presentation. Based on these 3 main pillars, over the years, we have had several applications in the space of automotive design, aerospace design, additive manufacturing, biomedical engineering, as well as electrochemistry and even supply chain management. And I will try to show you examples of how machine learning and artificial intelligence can actually impact all these seemingly disparate fields in pretty similar fashion. So The bulk of the talk is going to be to show my belief in how ML and AI will actually change how we do computation and engineering at large. So if we look at the traditional mechanical engineering pipeline, and if we were to cluster it into the three main groups, you can call the very first step in engineering design as the generative design phase, where humans typically do conceptual design. They may take an existing design and redesign it. They may look at past repositories of design to come up with an abstraction of the design problem that they're working on. And that leads to a lot of conceptual design, early exploration, and so forth. Then comes what we know as the traditional computer-aided design. Once we have the ideas in place, we go to the computer, we sketch them up, we analyze them, we simulate them, we try to see how well we can manufacture them, how much will it cost, and finally we commit to that design and send it to production planning and manufacturing. So this is the very traditional design and engineering pipeline. And over the years, obviously, over the last few decades, there are many software companies that have come in and impacted primarily this middle section of the pipeline, which is the CAD side optimization and synthesis of the mechanical products. However, in the last 10 to 20 years, we're now seeing a lot of interest in new ways of doing engineering, primarily because we have now new advances in advanced manufacturing, such as additive manufacturing. Complex shapes are much easier to deal with, much easier to manufacture. And over the years, people have actually created very large databases of data. So we have now a lot of existing designs, past designs, that we can actually look up and learn from in order to do further engineering and further design. So this has led to a very wide interest in early stages of the mechanical design process, whereas we do a lot of the generative design in the human brain. Now we are now trying to replace that creative side of the design with software. So in fact, a lot of existing software companies are producing new modules and methods that actually target this early design phase. And in fact, machine learning and AI is being used in this early design phase, as you may have seen in multiple Autodesk products and Siemens products and Autodesk, Fusion products, for instance. However, what we're looking at is in the next decade or so, we will see much more strongly the infusion of ML and AI into this design pipeline. So we will see ML and AI coming in the optimization, in the shape generation, not only in the early stages, but in the middle stages, doing automatic cost analysis, doing automatic supply chain management, and doing automatic manufacturing planning and manufacturing quality assurance. So there is a reason for why we expect ML AI to now actually have this huge impact across the entire pipeline. The main reasons why we think this is going to happen is ML and AI is actually very good at discovering complex patterns beyond human intuition. So it can accelerate, AI can actually accelerate what is called the typical inner loop in the design process. Any design process has this internal loop where you're actually analyzing the current hypothesis. You're trying to evaluate the current proposal. This goes as objective function evaluation or in other names, but this typically involves analysis. What ML is now promising us is a very fast way of doing this analysis. So replacing finite element method with very fast analysis methods, even though it may not be 100% accurate, the fidelity that we can now achieve with these ML-based systems makes these very, very attractive for the outer loop, which is the design cycle. Also, AI and ML is scalable. So solving combinatorial problems, sequential problems, iterative decision-making problems, which is very, very difficult for humans to do in a scaled-up fashion, computers and machine learning is actually is proving to be very, very powerful in this aspect. Also, when the physics of the problem that we're investigating is only partially observable or intractable or is intrusive, machine learning is promising new ways of doing this physics without having to do the full-fledged, full observation of a model, for instance. So there are very, very interesting developments such as PINs and other developments in the biomedical field that actually allow ML to actually make significant strides towards real results. Also, once an ML system is trained, it has typically a very impressive real-time performance. And if it doesn't, the typical reason for why it may not be is in the early stages of feature extraction. So it can be concluded that if the feature extraction itself is relatively efficient, the real-time performance of machine learning models are very, very impressive, very fast, allowing real-time monitoring and quality assurance. Finally, machine learning has the advantage of being able to learn patterns and tacit assumptions and design rules through human interaction and by observing human preferences. So this creates a very, very powerful method where by monitoring human activity over a long period of time, a machine learning system can be trained to perform similar to how human designers can perform. So in today's talk, I wanted to highlight some of these ideas, some of these reasonings through examples from my research. So I'm going to show you a few separate different application scenarios where ML and AI is actually being used to either accelerate or create new designs that humans cannot come up with easily. And as we walk through these slides, I hope you will see that common denominator of being able to do things fast at the expense of having to perhaps train such systems in an offline setting. So let's talk about generative design. So this is the idea of taking a design problem for which the requirements are set, but you're trying to achieve an objective. So you may be looking to create very lightweight structures, right? So if you look at what is called generative design or topology optimization, we currently have tools that can create very organic looking structures similar to how our biological, for instance, bone structures may actually develop over time. And there might be other objective functions that you can assign to it. It could be the compliance maximization or minimization or lightweighting, minimizing the mass and so forth. And this field is becoming very, very popular with the advances in additive manufacturing. And you will see in popular science now major applications in aerospace and automotive. However, this topology optimization generative design can be very slow depending on the resolution that you're striving for. And it's hard to scale up this approach to complex force configuration and objective functions for the design process. And once you design something, it not only needs to have an engineering specification that you're meeting, but also it has to be relatively inexpensive to produce. And unfortunately, a lot of the topology design results, generative design results, even though they look very, very functional, they can be very difficult to produce in cost-effective ways. So there's really an open gap in being able to do this. And as one example towards this, I want to highlight a work that we have done with Professor Jim McCann here at CMU, with a collaboration across Lockheed Martin, Siemens, and Automated Dynamics. The problem we're looking at is actually creating internal, what are called structures for automated fiber placement processes. So automated fiber placement is a process of laying down fibers or fiber reinforced tape as the skin of a flying object. So you want the internal structure that carries the skin to be as light as possible. However, it turns out that this is a massively complex problem because the manufacturing process itself involves very large forces applied to a common internal core structure. And a geometric limitation, this structure has to be later removed because as it currently stands, it's a very, very heavy part of the design. So typically you use a steel core structure and then you put the fiber, automated fiber placement on top of it. However, the one requirement is that this core can be slid out of the final cured skin, which limits the types of designs that you can make. So instead, what is desirable is to create what are called flyaway core structures. So if you can make the core structure as light as possible, you can actually keep that in the structure and then have it be a flyaway core. So this turns out to be a mathematically very, very challenging problem because you have to do topology optimization, which in itself is a very expensive process, possibly thousands of times iteratively. And I'm not going to get into the reasons why that's the case, but when the forces for the manufacturing forces are moving across the surface of the part, this becomes a very, very intractable problem. And it turns out that we can use ML to actually accelerate the search for the optimal shapes in this very, very challenging scenarios. And if we did not have ML, I think many of you can envision that the way to actually solve this problem would be for any internal structure that you can create, you may have to simulate all the fiber placement forces by actually moving a force across the surface and then doing a full-fledged finite element analysis. This is going to be awfully, awfully slow. What ML allows us to do is, given an internal structure, it very quickly tells us what the most critical part of the entire system, where that would be, and how much force can it actually withstand. So we can actually accelerate the search. We're not coming up more accurate solutions, but we're actually accelerating the search by orders of magnitude using machine learning. And at the heart of this is actually a concept that's very traditional, which is design of experiments and being able to choose these points in a very meaningful way. Again, I'm not going to get into the details, but through machine learning and design of experiments, we actually find very informative points on which simulations should be run, which gives us a big picture view of what the most critical places on the structure can be and how we can actually design internal structures to mitigate any failures. And with this, we can actually do only 1 to 2% of the entire possible force location simulations. So we actually significantly reduce the amount of simulations that is needed through machine learning. And out of this comes, interesting internal structures. We're going from over 100,000 degrees of freedom to 15 degrees of freedom through dimensionality reduction, which allows us to design internal structures at different levels of detail. And as a proof of concept, we actually collaborated in an America Makes project with automated dynamics to create these aerospace structures. And we have achieved significant reductions in mass. And we actually tested whether this will truly withstand the forces that are coming through. And it turns out that it does indeed withstand all these massive amounts of forces that are being applied to the surface. So these structures are lightweight structures, guaranteed to withstand the forces that are coming up from the mechanical domain. Similarly, another demonstration of the similar principles of designing core structures through ML and being able to withstand dynamic forces that are applied during the manufacturing process. So we were very happy to see, even with a factor of safety of 1, we did not have any failure throughout the production cycle here. Very closely tied to this is the idea of minimizing the cost as well as minimizing the weight. So simultaneously minimizing cost and weight. It turns out that there's a trade-off between cost and weight. You cannot, you have to trade off one to minimize the other and vice versa. And this is a collaboration with Professor Katie Whitefoot in our mechanical engineering department. But we have discovered interesting trade-offs where the cheapest structure to manufacture may not be the lightest structure. In fact, the system prefers to create a little bit more mass because that actually has an impact on the additive manufacturing machine utilities, for instance, electric usage, power usage, and so forth. So the lightest weight structure may not be the most cost-efficient structure. So we are able to now play with these Pareto optimal solutions in order to give designers a portfolio of designs that they can choose from. Next, related to this topic of manufacturing through or designing through machine learning, I want to bring something that I think many of you are familiar with, which is the deep fake idea, right? So people are using very impressive neural approaches to generate new content. For instance, on the left is a paper by NVIDIA in which they create synthetic human faces. So the human faces that you see here are not real. So these are generated by a computer. Likewise, on the right is a system that can take actually a painting from famous painters, turn it into a photograph, or take a photo and stylize it in the style of a particular painter, for instance. So at the heart of all these very, very impressive methods is a neural approach, a neural network approach, and specifically a generative adversarial network. It's a very interesting concept in which there are two neural networks that are competing against each other, a generator and a discriminator, and you're actually training them jointly in order to create a very strong generator, which is denoted as G. And we have been inspired by these advances and to bring these into the space of engineering design. In fact, we have recently published a work in topology design, so automatically designing the structures that I mentioned before in a split second, in less than 1 second. Normally, these can take actually a few hours to a few days by using generative adversarial networks. The idea is to train a machine learning system with a lot of data, different boundary conditions, different force loading conditions. So you give the system different examples in an offline setting, and what the system is able to do is use this training as a way to learn how to do topology optimization. Again, details aside, the final product of this is a single system that can actually generate structures under different design requirements. For instance, each row here is a different design requirement, different boundary conditions, and different loads. And in the right column, you see the ground truth, what would normally be coming out of a topology optimization method. And on the left is our system actually learning how to design these. The training for these can take quite a bit of time, a few days on several GPUs. But once they're trained, they can generate a solution very, very fast in less than a second. So the power of machine learning is not so much that it's a magical tool, but it allows you to take all that computation in an offline setting, train a system well in that setting, but then have very fast performance during deployment. And here are some examples, further examples of how our system can actually do designs, topology designs, and you can see that it is actually providing pretty good solutions compared to the ground truth counterparts here. The same principles, even though those examples were in 2D, they actually extend to 3D in a very similar fashion. So the machine learning really does not pay attention to whether the data is in 2D or 3D. It's very similar architectures, very similar approaches can be used to scale it up into realistic settings. Likewise, in a similar spirit, we're actually using a very similar concept of a generative adversarial network in order to do very fast analysis. So if you have done any stress analysis using a finite element package, you can appreciate how difficult it is to set up a mesh to actually do convergence studies. It takes a lot of expertise to run a finite element package. So what we do here is we train a similar system that can do stress analysis in a split second, again, using offline training. And it can actually work on previously unseen geometries with complex internal structures. The right-hand side column is, again, what you would expect out of a classical software. And this column, called the stress scan, is the result of what our system can produce. This was a joint work between our lab and Professor Amir Farimani's lab, who's also in the mechanical engineering department. Tied to, again, this manufacturing and is the collaboration we had with Boeing, where they were trying to redesign a fairing, an aircraft fairing. And the traditional way, which has been a very old design for the last 40 years or so, involved 48 components and 87 different interfaces where all these different components would be assembled together. the question was, which parts can be consolidated? Because we can potentially use additive manufacturing to produce these, and the shape complexity is not a concern anymore. And if they are consolidated, how should they be printed? And it turns out that this is, again, a very difficult problem. There are 2 to the power 87 different possible solutions to this problem. It's a combinatorial problem, very, very challenging to solve this through heuristics. But using, again, advanced methods, we're able to generate solutions for which the system automatically tells us which parts should be consolidated. And not only that, those consolidated parts, how should they be arranged in a 3D printer? How should we actually arrange all that information or all the parts that we have consolidated into different 3D printers? In fact, we can have multiple different batches of printers that are running in parallel, and the system automatically configures this for us in a short period of time. We can also produce, as a byproduct of this, the total cost of producing, for instance, a production unit of 100 different fairings, and we get very quick cost estimates based on this advanced approach. Okay. Again, similar to this topic, tied to this topic is what we're currently working on with Professor Whitefoot's group which is changing the design, not only consolidating legacy designs, the different parts into consolidated parts, but also redesigning the parts. So we are now extending that work and using what is called neural optimization, using the backpropagation and auto differentiation properties of neural networks in order to automatically redesign legacy designs from scratch. And we can impose the number of different parts we want. The system automatically tells us what should be each part and what should be the configuration of it, in what orientation should it be printed, and so forth. So it can automatically generate a whole bunch of very interesting mechanical solutions that a human designer may not be able to come up with by themselves. So we are seeing a very interesting impact of machine learning and AI in the design and analysis of these structures. Okay. Finally, this was the last project I wanted to bring. Again, this is in the additive space, and this is a collaboration between our lab and Professor Jack Booth's lab. This is the impact of ML and AI for real-time process monitoring, quality assurance, and flaw detection. In additive manufacturing, it turns out that the metal additive is a very finicky process. It's not trivial to run these machines, and a lot of things can go wrong. At the top, for instance, you're seeing 2 types of defects that are very common in metals additive, which is called, one is lack of fusion, the other one is the keyhole porosity. These happen either because the laser is too slow, it's not powerful, or it's too fast and too powerful, for instance. So due to these different variations in the process, you can actually induce quite a bit of flaws. So the question is, can we automatically detect these by simply listening to the Beal chamber? And this is how it actually sounds like. So as you can hear, the machine itself is emitting a lot of interesting acoustic signals around. And it turns out that you can detect whether a flaw happens or not by carefully listening and training a machine learning system that can distinguish between what is a flaw-free build versus a flawed, for instance, instance. And we are actually utilizing now this idea in order to train a machine learning system that can use acoustic signatures as a way to do real-time process monitoring and fault detection. And for that, if you look at the entire build volume, we put a very inexpensive sensor at the very top of the build chamber. It looks pretty much like this. And we train a system. We induce different flaws in an offline setting. We get the time signal. We turn that into a frequency domain spectral transformation, turns into an image, and we train, again, a deep neural network in order to do this classification. And remarkably, the machine can do this very, very accurately. We're achieving close to 99% accuracy in this 4-class classification problem. But once it's trained, it can actually do real-time monitoring. Once you train such a system, you can do automatic fault detection in real time. And here's a demonstration of that. The earlier phases are very slow, but then you'll see the real-time speed as we go towards the end. You know, the time signal comes in, we do the feature extraction, spectrogram transformation, and then passing that information through our neural network, very quick responses. And we can actually do this real-time classification for monitoring and additive manufacturing process. And this is the real-time speed of how decisions are made so quickly. So with this, you don't have to have a human operator kind of listening, constantly monitoring a build chamber, but you can have a machine actually help you along the way and in real time throw a flag if things are just getting out of whack, for instance. So in conclusion, moving forward, so where do we see machine learning and AI actually making a difference? I think we're headed towards a new trend in machine learning aided design, not only computer aided design, but machine learning aided design, in which the only thing that the human has to focus on are the design requirements. Everything else that we typically have humans do, for instance, geometry generation, selecting the production method, understanding what the current materials are and how to resource them, understanding the issues with the supply chain, and optimizing for that, you know, figuring out the cost, all of these can be a byproduct of an ML-aided design. So a human does not need to deal with these. And I think we're headed in that direction with the power of ML. In fact, the design, as we know, as a geometry, should no longer be what the human touches. A geometry, the shape, should be the product of the requirements that the humans are putting forth. Also, with many interesting advances in what is called physically informed neural networks, I think we're headed in a direction where classical finite element solvers, partial differential equation solvers, will be replaced with neural networks. We will no longer need to do 3D meshing, for instance, and pins can actually solve very complex problems through simply point sampling, for instance. And there's a lot of very interesting developments in the space of neural approaches to doing engineering analysis. One of the biggest impacts that I see is real-time monitoring, quality control, and forecasting, which is what people call digital twins nowadays. But this is going to have a huge impact in different sectors like transportation, supply chain management, manufacturing, healthcare, and financial markets, and environmental, atmospheric, for instance, monitoring. So the promise that we see in ML and how fast it can actually do these things and how powerful they are, I think will have a huge impact on many, many different sectors of our parts of our lives. Finally, so the impact of such developments on the labor markets, intellectual property, ethics, policymaking, and accountability, is not trivial. So there's a lot of people working on all these different aspects, not only engineers, not only computer scientists, but philosophers are now involved in these. But it's a big, big space in which, things will be changing very, very rapidly. So it's an exciting future, but it's something we also need to study, understand, and hopefully have our hands in shaping this future. Thank you very much for your attention, and I'll be happy to take any questions.
Great. Thank you so much, Burak, for such a thought-provoking presentation. Hi, everyone. My name is Nikki Wolford, and I am the Director of Development in the College of Engineering, and I'm so excited to be here today to moderate the Q&A session of today's webinar. Just as a reminder, if you haven't already done so, you can submit questions via the Q&A feature at the bottom of the screen. So first, Burak, what labs specifically on CMU's Pittsburgh campus are doing this work, and where are they located?
there are multiple different labs. In fact, at least for the mechanical engineering, I can say that there may be pretty much 95 to 100% of the labs in the mechanical engineering department are somehow touching upon machine learning. So it's very difficult to kind of carve out hard boundaries in which this is happening. I'll be more than happy to provide names and pointers to all the labs that I'm aware of within, computer science, machine learning, the CIT and the engineering college, where very active machine learning projects are going on. But there's a very wide spectrum of labs that are working on these problems. I'll be happy to provide that in writing after this talk.
Wonderful, thank you. And then we got a couple of questions that are very similar to this. So basically how we are taking this into the classroom to prepare CMU students and our future engineers.
Oh yeah, so historically, CMU has been a wonderful place where the synergy between computer science and engineering college has existed for decades now. And we are seeing a lot of interest in machine learning, artificial intelligence, both from the machine learning department, the computer science, School of Computer Science, as well as the College of Engineering. So there are many, many different courses offered across the campus. And many different departments are now coming on board, non-ML departments, non-computer science departments, offering their own courses in machine learning. In fact, in our department, myself included, our professors have been teaching AI ML for over 10 years now. So we have a very strong and prevalent set of courses, robust courses in the space of applied ML in the College of Engineering, not only in mechanical engineering, but across multiple different departments, as well as core machine learning courses that are offered through the machine learning department. So if you want to do theory or applied machine learning, there are a whole bunch of courses at CMU that are here to provide that service.
Great, thank you. And then another question we have here, very interesting. What kind of community benefits can this work bring, perhaps in the biomedical world?
Yeah, that's an interesting question. The community benefit, I'll just interpret that, but I think there's a significant potential in individualized healthcare. And we're seeing evidence of that with our wearable devices now monitoring us all the time, basically giving us plots and scores of how our health is. I think this is going to become very pervasive, not only for simple measurables on the outside, but for a whole bunch of things on our internals. In fact, if you follow Yuval Harari, he's a philosopher, a person who speaks about the future. He's from Israel. He has this fascinating Google talk where he talks about how we currently seek healthcare when something is wrong with our bodies, right? So the first time that we actually personally detect that something is wrong, we go and seek healthcare. But I think that we're headed in a direction where even before we realize that something is wrong, all the sensors that we will be wearing on our bodies and things that we will be putting in our heads, they can tell us if we're headed in the wrong direction, if something bad is about to happen to us, and how we can actually change course. So I do see a lot of potential in individualized medical care, not at the point of healthcare providing healthcare when things are bad, but long before, in terms of diagnosing things or forecasting how things can go. So I do see that is made available by machine learning to be a very interesting thing to take advantage of. And what's coming up next for my lab, is that the next question we see?
Yes, yes. So we just have one more question, but if audience members have any more questions, please go ahead and submit them. But yes, what is coming up next for your lab?
Yeah, so we're working on several different projects, but at least surrounding what is, about the topics that I just talked about here. We are now investigating, we're collaborating with an outside company in being able to do or realize this ML CAD, right? So being able to do machine learning for CAD altogether. So can we go from design requirements into a machine learning system automatically deciding what the design should look like, how it should be manufactured, should it be additive, should it be subtractive, should it be hybrid, where should it be made? Should it be made in-house? Should we actually send it somewhere else? How much is it going to cost? So the whole pipeline in design and manufacturing, we are hoping to actually take a stab at completely automating this process. So we are interested in this. It's still in the work, so we don't have a lot to share at this point, but a lot of thinking has happened with my lab and multiple different labs across the campus, including the Next Manufacturing Institute.
Great. And actually, we just got another question in. So is there a way to train our models faster while not losing much performance? So as training for multiple days with multiple GPUs are not always available?
That's a very good question. And this is really at the heart of the hardcore research that's going on in the machine learning community, right? So we want to be able to learn from as few examples as possible, and we want our models to be still as robust as possible. I can say that there's a lot of literature currently that exists that show how to choose your training data intelligently. So it's not so much about maybe accelerating the neural network, the training time or so forth, but really picking the right data to train your system on. So there's a lot of work in automatically adapting the choice of your training data based on the past data that you have and internal validation systems that you're running with your model. But yes, that's a very relevant question, very important question. And there's a lot of work that goes in that field. Another thing that people are actively working on is what is called transfer learning and domain adaptation. What this means is being able to train a machine learning system in one context, in one domain where maybe data may be abundant, but use that trained model, maybe take a partially trained part of it, maybe the earlier stages of the neural network, for instance, and then train on top of that, add the data, the scarce, limited amount of data that may be available for your specific problem. And people have shown an impressive amount of robustness of these machine learning systems where you can actually train it in one context and bring it to another context to really still perform at a high level. I think these two approaches, careful selection of the data points combined with domain adaptation and transfer learning, I think can actually be the answer to this challenge.
Now, this might actually be a follow-up question to that. So where do you get your training data from?
Well, if you have, I don't know if it was intended for me, if it was for the examples that I have shown, we actually resort to, different CAD repositories. We learn from 3D geometries that have been done before. In cases where we're doing, for instance, analysis or topology design, we actually create tons of synthetic data in our an offline setting by ourselves. So this is something that we do in-house. But if the question is, where do you get the data for instance, things like transfer learning or domain adaptation, I think that might be a slightly different question. And for that, it all comes down to finding the similarities, analogies between what your problem might be calling for versus what that original large data domain may have actually produced. For instance, if you're doing an engineering problem where you're processing images, it has been shown that by training or pre-training an ML system based on massive amounts of existing data in image repositories, you can actually learn interesting, important features if it's a bunch of natural scenes, for instance, and your problem involves natural images where there's natural objects. People have shown that the massive amounts of data that's available in one place, you can actually pre-train a model and bring it to a new model. If it's in material science, for instance, material discovery, people have shown, again, very similar performance improvements where instead of having to train something from scratch for a material engineering synthesis domain, for instance, you can use pre-trained machine learning systems in order to bring it to this new domain. So there are many, many examples of this, but the short answer to that question is, large repositories of data, people actually training this with synthetic data that they generate in-house or through using, widely available data sets, and then adapting those to a new problem.
Great, thank you, Burak. I think that is all the questions that we have for this afternoon. So thank you again, Burak, for a very thought-provoking and informative program. I also wanted to thank our audience for participating today. I hope you will be able to join us at our future Faculty Insights programs. Please keep an eye out for a follow-up email soon, which will include a link for the recording from this session. Thank you again, and have a wonderful afternoon.
Thank you very much.